All right, what's going on? Hello, bonjour, welcome. Hopefully everybody can hear me. Everyone online can hear me. We ran into some technical difficulties, so I had some slides here. We're about nine minutes over, so we're just not going to do the slides. But I'm just going to basically tell you what we're going to be talking about today. So today we're going to be talking about building minimal DeFi applications. And if I had some slides, I would show you some wonderful pictures, but tough luck. And with building minimal DeFi applications, we're going to be talking about the current major DeFi projects, some of the major functions that they all use, that they all share, and then we're going to go over this DeFi minimal repo that we've been working on, and then we're going to do a little code along. So since we have a small enough group here, which is great, we can be pretty interactive. So, and before we get started, how many people here are developers, coders? Oh, yes. Okay. How many people here are DeFi coders and have worked with DeFi, understand? Yes. Okay, excellent. All right, cool. How many people here are new coders to Web3, brand new to Web3? No, you're not. What? All right, cool. So how many people are more experienced, intermediate DeFi developers? Okay, how many people are experienced DeFi developers? So there was a ton of people who were developers, but very few DeFi developers. Are most people here Web2 developers? Are you a Web2 developer? Raise your hand. Okay, cool. All right, so that gives me an approximation. Okay, cool. And again, you can't say anything. So right now, the major DeFi applications are projects like MakerDAO, Lido, Aave, Uniswap, Curve. These are all the kind of the big DeFi applications. And they have some similar functions. They do some of the same things. Some of the main things that they do, and pretty much most of them share, is some type of deposit and withdraw collateral or assets or et cetera. Right? So understanding how to stake, add liquidity, deposit. These are all basically functions that do essentially the same thing. It's going to be taking your ERC token and locking it into your smart contract, and then doing obviously the reverse of that, which is going to be withdrawing your ERC20 token or your native ETH, your native Polygon, your native Avalanche, your native blockchain token. And then a lot of these protocols will have like a get value, maybe a claim reward if you're doing staking or yield farming, a borrow repay, a swap, mint burn, depending obviously on the DeFi application. So today we're going to be doing a minimal Aave, so a minimal lending application. We're going to be coding it live, and hopefully my coding goes smoother than our AV setting up. And since we have a small group, please raise your hand, ask questions, and we're going to be jumping right into it. So I have like a couple slides to say what Aave is, but you can't see any of the slides. So Aave is a borrowing and lending protocol. It's a way for you to put down some collateral, and in return, you're able to borrow assets. And why would you ever want to do that? Well, one of the major reasons is to leverage exposure to certain positions. If you're confused on what that means, do a quick Google search on like leveraging or short selling. That'll give you kind of the basic breakdown. It's basically a way to say, hey, I have some money in Ethereum. I don't want to sell my Ethereum, so I'm going to put it down as collateral. I'm going to borrow some asset and buy more Ethereum with that borrowed asset, so that now I have basically doubled my exposure to Ethereum. If the price goes up, I make double the profit. If the price goes down, I lose twice as much as well, approximately. And I was going to let people choose which framework we were going to work with, Brownie, Foundry, or Hardhat, but I'm on a setup that I'm not familiar with, so it has Yarn, so we're going to go with Yarn here. But let's say I was going to ask that question. How many people here would be like, yes, Brownie, I love Brownie, let's do Brownie? All right, cool, some Python people. How many people would be like, Foundry, give me those Solidity scripts, love, okay, cool. Didn't you also vote for Brownie? And then how many people would be like, Hardhat, love me some JavaScript? Okay, so JavaScript would have won anyways. All right, so this works out well. And the hard part of this is, since I need to hold the mic while coding, we're going to enter a little stance here and see how this works. All right, good? I think this is good. How weirdly can I hunch over? Ta-da. All right. All right, let's do this. So and I gotta pull up my code base here so I can see what I'm doing. Yeah, everyone taking photos. Let's do this. So Let's get started. Let's create our hard hat project with yarn hard hat. Hard hat's not installed, so we need to install hard hat. Yarn add hard hat. Oh, thank goodness, yarn is working. Okay, cool. So we're going to be using hard hat. We're not going to actually do a lot of functionality with hard hat. We're just going to be, using it as our scaffolding for it able to compile. If we have time at the end, we'll write some tests, but we probably won't because I've already, wasted 15 minutes setting up. So, and for anybody who wants to see this, I don't feel safe going to the internet right now, so so I'm just going to tell you. If you go to github.com, smart contract kit/DeFi minimal, we have all the code here. So if you got confused or if you want to play with this later, you can go to that repo. If you're watching live, you can go to right now, follow along with us. And it has a ton of different examples. So it's got an Aave example, synthetic staking example, reward token example. It's got some Aave Uniswap examples. It's a living, breathing repo of just really condensed classic DeFi applications. So I'm working on a stablecoin one right now. So hopefully that will be out soonish. So we'll do yarn hard hat. We'll get our hard hat project set up. Create a JavaScript project. Yep. README already exists. Oh, sorry, because I'm in the middle of another project. JavaScript project. Yep. Right, okay, so we're going to do CD. We're going to CD down one. Sorry, CD down again. CD, let's just CD. Let's see if this works. All right, can I like turn off the screen for a second? Steven, can I go to your home directory? Probably not, right? That's probably it. Okay. I really don't want to. Dude, new workspace? Okay. File. New open workspace? Is there a new workspace button? Sorry, guys. In the workspace folder.
Just go up 2 directories.
Go up 2 directories? Yeah, right? Everyone's just going to see all of Steven's files. Sorry. Workspace? And then new folder? Okay. Okay, all right. Here we go. You're going to trust me. Thank you. All right, cool. Now we're going to try again. And thanks for bearing with us, everybody who's watching and everybody who's here. But we're going to be doing some really cool stuff, so. All right, yarn, hard hat, here we go. There we go, this looks more right. All right, cool. So we're downloading hard hat, and again, this is just our scaffolding for the code that we're building. We're barely gonna interact with it. And we have a little lock.sol, which is cute. And I'm also gonna grab the hard hat solidity extension. For those of you who are working with VS Code, never mind, we're not going to install that. But for people who are working with VS Code, the hard hat solidity extension is really, really nice. It makes your solidity get formatted, have the code highlighting, so that's kind of cool to show anyways. But the Juan Blanco one is also really good. Hey, whoa. Merci. Oh, this is actually worse, because now I can't get the mic. I think I'm going to use that one. We're going to be showing you guys cool stuff, I promise. This is better. This is much better. All right, cool. Now stuff's highlighted. All right, great. So time to actually build our contract. So we're going to go to our contracts folder, new file. We're going to call it lending.sol. And let's get rid of lock.sol. Delete. Goodbye. Lending.sol. Okay. So classic setup, we'll do SPDX license identifier. MIT, pragma solidity. 0.8.7. Hopefully they can still hear me. Contract lending. All right, cool. Downloading the compiler, which is great. While that downloads, let's just create the basic functions that we're going to need to do. So we're in our contract. We have our minimal contract here. What do we want this to do? So we want this to be able to deposit collateral, right? So we'll do function deposit. What else do we want it to do? Function withdraw. We want to be able to deposit our collateral so that we can borrow. We want to be able to withdraw our collateral so we can take it out. We're going to want to be able to borrow because this is going to be a borrowing and lending protocol. And then we're going to want to be able to repay. So these are going to be the really bare bones functions that we're going to be doing. And this deposit and withdraw, these are going to be kind of the most important functions, and understanding how these work and how to use them will help you in pretty much any DeFi application you make, be it borrowing and lending, being swapping, whatever, right? Because you're always going to need to lock some type of asset in your smart contracts, right? Because it's a smart contract that's going to facilitate all the logics of your financial assets. So let's start with deposit here. So this deposit function, and then actually let me add these in here so that stuff actually compiles. And then we'll make this external, make all these external. Cool. So our deposit function is going to be an external function, right? Because nobody in our contract is actually going to be calling it. And when we deposit, what are we going to be depositing? Well, we need an address token. What token are we going to be depositing? What's the asset? Is it the WETH wrap token, et cetera? And then obviously, UNT 256 amount. Now, when we're depositing, we want to make sure that we do the transfer call when we transfer the ERC20 tokens. And for everybody who's here, an ERC20 token is just another smart contract. When we call that transfer, that's got to be the last step in this function. So I'm just going to go ahead and write it now, though. So we'll do bool success equals something something dot transfer from message dot sender address this. Oops. Amount. And since we're doing an ERC20 here, push this over a little bit. Oh, okay. Since we're doing an ERC20 here, we're going to need an ERC20 interface. So we're going to import that from OpenZeppelin. Oops. Import OpenZeppelin /contracts. C, oops. Token, ERC20, IERC20.sol. I can type much faster when I'm sitting normally, I swear. So now we have the interface for an ERC20 token, and we can just wrap the address of the token, IERC20 token, that transfer from message.sender. And this will transfer the token to this contract, and then we just say, if that transfer was not successful, sorry, and the mic is now on a rogue rampage, there we go. If the transfer was not successful, then we're just going to do a little revert, and we'll say transfer failed. And that means at the top, we're going to do a little error code outside of the contract. We'll do error transfer failed. And because of my weird setup here, we're probably going to just go over these fundamentals and not everything. Do a little compile, see if that looks okay. Gotta add that, yarn add. Opens up in contracts. Okay, cool. Compile. Shit. Whoops. Yarn hard hat compile. What's mad about not finding hard hat? Oops. Guess we'll just doubly make sure it's installed. All right, now it's doubly installed, I guess, but it's compiling successfully. Yay. So, all right, so now that we have this compiled, we have this kind of very minimal deposit here. Does anyone see anything wrong with this deposit, or are we missing anything? If we're building a contract that's going to keep track of people's collateral, we now have a way to get the tokens. What are we missing here? Balance. There's no mapping. We're actually not keeping track of anyone's collateral here. So we're depositing tokens to keep track of collateral, and we don't have a way to do that. So what we want to do is we're going to create a mapping towards the top that's going to be a mapping of users' accounts to these token addresses to how much assets they actually have. So up at the top, we'll do a little mapping, and it'll be a mapping of an address to a mapping of an address to a UNT 256. We'll make this public. That's not the best, but it's fine. And we'll call it account to token to amount. Great. So before we do the transfer here, we'll do account to token to amount of account to token is going to plus equal amount. Cool. All right, so now we're keeping track of how much people are sending. Is there anything else wrong here or missing? So we're keeping track of the balance. We're sending the tokens to this contract. We're locking them in here. And I spelled account wrong. Account is not defined. Yep, sorry. This should be, yep, message sender. Sorry, yep. Is there anything else wrong here? Does this deposit function look okay? What do we think? We don't worry about that in this contract. That's something the front end would do. Anything else here? All right, I'll tell you, it looks pretty good. This is pretty much it, actually. There's some additional things that we probably would add if we had more time. Like we would definitely want to emit an event saying, hey, a mapping's been updated. We'd have maybe some modifiers saying, this token is allowed, because we don't want to just be able to accept any ERC20. We're not going to have a price feed for every single ERC20. And we might want to do a modifier like non-reentrant to get rid of reentrancies or more than 0. But basically, this is it, right? And which is really cool, because for all of these DeFi applications, if you want to make one of these deposit collateral stake, add liquidity, this is essentially it. Send the token and keep track of how many tokens are being sent. Boom, you've just done like 50% of all DeFi applications. and now someone's going to be like, oh, Patrick told me this was 50%. The second 50 is much harder. All right, so great. So next we would add a withdraw. I'm going to skip the withdrawing just to go right to borrowing, because withdraw is basically going to be the opposite of that, and I can't type very fast down here. So let's do borrowing. So now we have a way to deposit collateral. Other people are going to deposit assets into this smart contract, and we can say, hey, like, I have collateral. I would love to borrow that asset to do stuff with it. So we're going to do basically a check to make sure that you have enough collateral down to borrow the asset, right? So let's say I put 1 ETH down as collateral. and I want to borrow $50 of USDC, 1 ETH is going to be plenty. But let's say I put 1 ETH down as collateral, and I want to borrow $10 billion of USDC, our protocol should say, hey, you can't do that, right? Because your collateral doesn't cover that, right? Your collateral needs to be at least equal to how much you're going to borrow. Normally, it's over-collateralized where you want a lot more, but we're going to kind of skip that for now because we have, how much time do I have left? 20 minutes? 10 minutes? 25 minutes. Thank you, because I have 25 minutes left. So we're going to do borrowing now. So if I want to borrow something, obviously we need to give the address of the token and the amount that I want to borrow, UN256 amount. We'll make this external. Ideally, we would do some non-reentrants. Is the token allowed? More than 0 modifiers, but again, we're going to skip that for now. And again, this is going to be external because nobody in our contract should be calling this. So the first thing that we're going to need to check for is whether or not our contract has enough of that token, right? Because people are going to be depositing collateral. They're going to deposit, like let's say in our example, USDC. We need to check that, does our contract have enough people deposited the USDC? So normally I would do kind of this if, else revert, but require uses less typing, so I'm just going to do that here. So I'm going to say require that the ERC20 of the token dot balance of address this is greater than amount, and if not, we're going to say not enough deposited or not enough collateral or something like that. Want to check that we have enough of the token that they want to borrow. Next, we would probably emit an event or something like that. Then we would just send them the token, and we're going to have one more really, really important step, which makes this kind of whole thing to come together. So we're going to do bool success again, equals ERC20 token dot transfer to message dot sender amount, and then we're going to say we're just going to do require success failed, and so this, we've basically just done the opposite. We're sending tokens to people who are borrowing, but what are we missing? What are we not doing here? Somebody says, hey, I would love to borrow, $100,000 of USDC, and we're going, yeah, sure, here you go. We are checking if USDC is in the contract, yes. Collateral. We're not checking for collateral. We have no idea if this person has enough collateral to take this out. They say, hey, let me borrow that USDC, please. We're saying, yeah, here you go. Thank you for stealing all of our money, which is not what we want to do. We want to stay solvent. So what we're going to need to do is build some type of function called health factor to check to see if they have enough collateral down. Normally, Aave calls this someone's health factor, and it needs to be above 1 at all times. If it's below 1, that's when people can come in and liquidate it. We're probably not going to have time to make a liquidate function, but we do have time to do a health factor function. So way down here, let's do function health factor. And this is going to be how we're going to make sure that they have enough collateral. And there's going to be some really interesting things here because we need to also price their collateral, right? If they put down ETH, USDC, BAT, Maker, DAI, all these different collaterals have different values. So we need to figure out what's their total value first so that we know how much they can borrow. So we're going to create this get health factor function, do address account. This will be a public view, and it's going to return a UN256, which we'll call HF, which stands for health factor. So the first thing that we're going to do is you're going to need to get how much money that they actually have. So we're going to create a new function actually called get account info, and I'm going to pass the account. And this is going to return a UN256 borrowed value in ETH and a UN256 collateral in ETH. Because we need to have them have the same unit, the same unit of measure, so that we know exactly how much value that they have. So we'll do a function, get account info, address account, and this will be a public view as well. And this is going to return those two numbers. It's going to be a UN256 borrowed value in ETH and a UN256 collateral in ETH. And I had no idea that my elbow could get so tired from holding this up this long. All right, cool. So get account info. And basically what we're going to do is we're going to loop through all of the possible collateral and see how much they've added up. Now, we don't have, we're not going to have time to like add like a, allow a collateral. So we're just going to cheat a little bit. Up at the top, we're just going to do an array, an address array called s_allowed tokens. And we're just going to hard code this. Normally we would add like a add allowed token, remove allowed token. This is like the collaterals that we allow on our protocol. If you go to Aave, most protocols have some type of like, hey, these are the ones that are not risky enough that we'll let them be collateral basically. And they have price feeds. So for this, for now, I'm just going to kind of dummy them as address zeros. So it's going to be 2 address zeros, but these are going to be like an ERC20 token address. We could put like the WETH token address, BAT token, etc. And then let me pause here. Is everyone following along, or are there any questions so far? Who here is like, I'm totally lost, I don't know where we are? Nobody's like that. Who here is like, I'm following, I'm with it, I know exactly what's happening? You're the one who was like, yeah, use Brownie and Foundry. Get screwed. Because I did the demo in Solidity. Although I have done a bunch of these in Viper. Next time. I do love Viper, just FYI. Okay, cool, so we're all following along, great. So we have this array of allowed tokens. So down here, we're basically just gonna loop through those in a little for loop, UN256. That was really just a way for me to rest my arm. UN256 index equals 0. Index is going to be less than s allowed tokens dot length. Index plus plus. Oops. Index plus plus. And now basically we're going to do UN256 amount equals s account to token borrows of user account. Oops, sorry. It's not account. What do we say? Account to, oh yeah, account to token amount. Token amount, that's what it's called. Yep, count to token amount. So we'll do account, and this will be s_allowed tokens. Actually, let's make this a little easier. Address token, allowed tokens of index and then we got to get the value uint 256 value in ETH is going to be, we're going to have to create a new function called get ETH value of the token and the amount. And then what we're going to do is we're going to do uint256 total collateral, oops, equals 0. And then outside of this, or excuse me, in here, we're going to do total collateral equals total collateral plus value in ETH. So we're going through this list of tokens. We're going to get, did I spell this wrong? Undeclared identifier. There's going to be typos all over the place here. Yeah, thank you. Account with an N. Ah, well, it's going to be quicker for me to just keep it spelled wrong.
I got a question.
Yes.
Does temporary variables create more gas?
It does. Yes. So if we wanted to optimize for gas, we wouldn't do this, but I'm optimizing for readability here. Yeah. Yeah. Great question. Really good question. Yeah. Cool. So we have this total collateral in ETH, and we're getting the value of our total collateral, and then we're going to have to get the value of our total borrows. And basically, we're going to say, okay, value of our collateral minus the value of your borrows. Boom. Do you have more collateral than you have borrowed? That's what we're going for here. So now we're going to go down here. We're going to do function. I have what, 9 minutes left? 9 minutes? Yes? 15. Even better. All right. Get ETH value. And then, yeah, as this gentleman over here did, if you have questions, just jump in. We have a small enough group, and it gives me a chance to not have my arms up, which works out really, really well. So we have to create this function, get value ETH. We're going to do the address of the token, and then the amount. So we can price their collateral. This will be a public views, returns, uint256. And here is where this kind of allowed tokens array is really important, right? In order to price our collateral, this isn't some information that we're going to find on chain, right? The price of your assets is something that us humans have just kind of assigned to things, right? We say the price of ETH is, $1,300 or whatever it is right now. The price of DAI is one. The price of the maker token is, whatever it is right now. That's not like some fundamental thing that lives on chain. That's something that we've assigned. So in order for us to work with that, we're going to need to work with an oracle. So we're going to import the Chainlink code in here, and we're going to read off of what's called a price feed. So if you want to learn more about how these price feeds work, how these oracles work, they're a decentralized network of Chainlink nodes, and they deliver data on chain so that we can use it in our DeFi applications like this one. So at the top, we're going to add some Chainlink code in here. We're going to do import at Chainlink /contracts /src /v 0.8 /interfaces Tor v3 interface. That's all. And with this interface, we're able to read from these price feeds, right? So this price information is already aggregated for us. All we got to do is read it off the contract, and this aggregator v3 interface allows us to do so. So we'll have to add this at Chainlink /contracts. Copy. While that's being added, way down here in this get ETH value, down here, we're now going to say aggregator v3 interface price feed equals, and this is where whenever we add one of these tokens, we're going to need to add the price feed associated with it, right? The price of ETH is going to have its own price feed. The price of BAT is going to have its own price feed. Price of Maker, et cetera, et cetera. So normally, again, we'd have like an add price feed with your tokens. We're just going to make it a little simpler here. We're just going to create a mapping of address to address, and we're going to call this s underscore token to price feed. Oops. token to price feed. And we're just going to assume for this demo that in the constructor, we say, okay, address 0 has price feed at address, XYZ. Address 2 has price feed at XYZ. But again, we're going to run out of time because I'm typing very slow. So we're just going to assume we already did that. This will still compile because all the addresses will just be 0 and all the price feeds will be 0. But if you want to get a list, you can go to docs.chain.link, Ethereum addresses, scroll down, and there's a plethora of data to choose from and price feeds to choose from. So we're going to say price feed equals aggregator v3 interface of s underscore token to price feed token. So now we have our price feed. And then we can just do, this is going to look a little weird. I'm going to give you I'm going to tell you why in a second. Int 256 price feed, comma, equals price feed dot latest round data. Oh, nice. Oops. Price. So price feed dot latest round data. Latest round data is a function that returns, I think, 5 variables. So we just put commas because we're not actually going to use them. So once we get this price, now what we do is we just say return the amount, and then we're going to times by 1 E18 because this amount is going to be, because we need to divide then by the price, divide by uint 256 price, like so. So, and the reason we're doing 1E18 first is because price is in units of way as well, so it has 18 zeros. Amount will also have 18 zeros. So we want to just multiply this by 18 zeros first so we don't cancel those out. So we get a result that still is in terms of way. Who is anyone unfamiliar with terms of way? Is this math like super weird to somebody? Who here is confused by the math here? Okay, great. Wow, you guys are all wizards. All right, cool. So now we have this function get.
Sorry, that's
Yeah.
the difference that you casted an integer into an assigned integer.
Sorry, what's the question?
The price comes in an assigned integer and you cast it to an unsigned. That creates some problem or not?
No, really good question. So we're just, in this function get ETH value, we're just returning it as a uint 256, but the Chainlink price feeds naturally return an int. So we just cast it as a uint 256. Yeah, it doesn't create any problems. If we had a negative price, that might be weird for sure. So if you wanted to be super like, if you were coding this for more professional use cases, you would definitely add some checks to make sure the int wasn't negative before you casted it. But really good point though, really good point. But again, this is demo code, so we're taking a couple of liberties here as you've been seeing. So cool. So now we have this get ETH price. Now we're reading from those price feeds, and boom, this function will now return. Oh, once I add a return in here, down at the bottom, we're just going to do return total collateral. Boom, like so. So now this is going to return. Return. Oh, okay. Actually, we're just going to do. We're going to cheat a little bit again. uint 256. Total borrows, because equals 0. Turn total collateral, total borrows. Thank you. For now, we're going to take a little bit of a liberty here. Oh, actually, I don't need this. So we would also roll through all of the borrows as well. So we're tracking how much collateral we have. We would additionally do this exact same process for the borrows and then just do the reverse, right? Get how much we have borrowed, and every time we take out a borrow, we would track that as well. We're going to do that. But again, in the interest of time, I'm just going to skip it because I have 5 minutes left, right? Okay, great. So now up here in our get account info, excuse me. We're getting our borrowed first. Total borrows, total collateral. We're getting our borrow, we're getting our collateral. And what we would do is we're going to adjust this for some liquidation threshold. So normally what these protocols do is they say, okay, you need at least 80% over collateralized or 50% over collateralized, or basically you need 120% to borrow 100%. Or if you have 1 ETH, you can borrow up to 0.8 ETH, right? You can borrow up to 80% of your collateral or 50% of your collateral or whatever that is. So we're going to do a little adjustment here. So we're going to say UNT 256 collateral adjusted equals, and then we're going to say collateral value in ETH times some liquidation threshold, which for us, we're just going to hard code it into this function. Normally you'd put it as like a global variable here. We're going to say it's 80. So we're giving an 80% threshold here. So if you have 1 ETH, you can borrow up to 0.8 ETH here. And then we're going to divide by 100 to make sure that our units of measure are correct. And then we just do return collateral adjusted times 1E18 divided by the borrowed value ETH. And now we have a health factor. Oops, divided by, excuse me, not the borrowed value, this one. And then we do some checking to like make sure, you know, if borrowed value to ETH was 0, for example, so we don't have divide by 0, but we're going to skip that for now. And now, up on our borrow, now that we've done all that, we've pretty much done the vast majority of the work we need to do to have our borrow function. So now here, we would just do require, the health factor of message.sender is greater than or equal to some minimum health factor, or we would just put 1 at the top. And we're good to go there. And the other thing we would do is we would track the borrows, kind of same as we did with the deposits, but like the reverse, so that below, and I'm just going to skip it for now. So this would be like account to token borrowed, so that again below, when we do this measuring, we just measure how much people have borrowed, but because I have 3 minutes left, we're going to skip it. But essentially, that's all you need for a borrow. Right? We would add some modifiers, maybe non-reentrant is allowed more than 0, where we check to see that the amount that we're looking to borrow is more than 0. If the token that we're looking for is actually in our token list, and some non-reentrant stuff so that people can't finagle with our stuff. But essentially, you have the bare bones here, right? You know how to price your collateral, and that's something that you're going to need in a ton of DeFi applications. If you're doing some type of staking and you're allowing many different types of tokens, you need to understand how much value people are staking. If you want to make a Uniswap, if you want to make a borrow lending, this is the super minimum amount of code that you need to do that. So yeah, because I'm sitting down here like this, I wasn't able to type as quickly, so we won't be able to go over the rest of it, but those are really the bare bones. That's kind of the functions there. Again, if you want to see the rest of this code, Smart Contract Kit /DeFi Minimal has all of this and more. It has a test suite as well, some deployment scripts in hard hat. Yeah, any other questions about any of this stuff?
Maybe just a remark that the health factor should be checked before the token is transferred.
Yes, you're right. The health factor should definitely be checked before the token is transferred. I put it at the end just to be like, make it more sense. But yes, that is a reentrancy risk. You would not want to do that. Excellent point. Yes.
Also, updating the internal status of the class, it's before making the effective transaction.
What's the question? Sorry.
So no, that actually the same happened with the updating the internal dictionary or map in terms of the amount, because it comes before the transfer. Because of the reentrancy attack, I understand.
So
updating
Yes.
the internal state of the object comes
Yes.
before the transactions.
yes, 100% correct. Yeah. So these parts where we call both of these lines, we should do these later. Yes, absolutely. We should do these at the end. So excellent point. Yes. Any other questions other than when Viper? All right, cool. Well, thank you all so much. Hope you learned something here. Like I said, feel free to go to smartcontractkit/DeFi, and it's open source. So if you want a specific thing, actually feel free to make an issue. Be like, hey, I want Viper, yeah, or ApeWorks for the ApeWorks team that's here. So cool. Well, thank you all so much.